Our third presenter is Adam Kankiewicz, known him for a really long time. Good to see you. From Black & Veatch. He's going to be presenting on modern PV plant capacity performance testing from an EPC's perspective. Thank you, Adam.
Thanks, Ian and Josh and everybody for the privilege to give a talk. For all you Kubrick fans out there, subtitle for this will be this. I want to acknowledge the BV solar performance team, Shale, Jay, and Prague as well. It takes a lot of work, as everybody's noted, to facilitate these performance guarantees and testing. Just a rough outline. Some performance testing overview. We've had Ben gave a good overview earlier, kind of build on that, some challenges. And then I'm going to talk about short-term energy testing, which is kind of a new fad. We're seeing pop up requests for this routinely now, and then a summary of what we're seeing. So performance testing itself. Just a quick background, Black & Veatch, we're a trusted IE, OE, and EPC partner. We have an extensive background with solar development, all aspects of it. Really cool employee-owned company as well. And we wear kind of two hats. We're kind of unique in the industry. We're a large EPC, solar EPC, as well as a mature and large. We do a lot of IE and work as well. This talk is be focused on the EPC side of the discussion, but it allows us to. It's unique and good in that we can cross-populate both sides with the information gained. So it's always good. So why performance test? It, again, as mentioned before, it allows you to get basically benchmark your plant's performance capabilities at the beginning, a starting point. These are used for both EPCs use them, owners need them for obligations. If you want to de-risk acquisitions for buyers, performance, financing, lending, etc. Consequences, failed performance tests can often trigger, as kind of Jim mentioned, you get some panic moments when a plant is not achieving expectations. These can trigger LDs or even make-right clauses within EPC contracts. So these are generally considered high-risk scenarios for EPCs. So one of my primary jobs is making sure that what we sign up for is achievable and realistic as an EPC. So when is performance testing? Don't worry, you don't need to know the details on here. This is a level 1 solar EPC schedule. This was for a very large plant. I think it's close to 800 megawatts DC. So that's 3 years along the bottom there represented. This EPC schedule covers 2.5 of those years. You have the substantial completion milestone noted there at the end. And our performance testing window is this little sliver at the very end that everybody is, everything's wrapping up, crescendoing big, and all of a sudden everybody wants this nice, package wrapped up with a nice performance test. It can be challenging. Just a quick review. Again, I'm not going to comment on the testing methods themselves. We're kind of agnostic, at least on the EPC side. We have to take whatever options, or whatever the contract specifies. So work with that. But from the ASTM perspective, simple. You define a target capacity, all based on typically a PV-SYST base energy model. You gather the site data, and that gives you your measured capacity. And then it's just a simple ratio of the two. And usually there's some kind of tolerance allowed for a guarantee capacity. We typically see this as the dominant performance testing method in the US. An example, this is, again, the regression. It's fairly straightforward. As Ben mentioned, challenges are filtering the data, and I'll allude to that a little later as well. But you take your data, it's just as straightforward as that. And here's an example test. There, you got your reference target conditions, your tested capacity, and this was a good, test that we'd like to see. Challenge in the industry is every little EPC contract we get, the testing exhibits, they always got some little twists in them, or they're not uniform. So you have to go through and, weed it out and bring some sanity to the picture once in a while, but it's always a challenge. Performance ratio testing, we don't see this as often, but we do have to deal with it as well. Similar concept, except now you're looking at, basically you're just taking a yield, an observed yield, and normalizing it by the incident irradiance. And then the weather corrected performance ratio is the standard one that we see run. Again, similar results. You just have to, your guaranteed ratio has to be above or your observed performance ratio has to be above a target ratio. And then you'll achieve success. This is not the dominant one in the US, but you go outside of the US, especially Europe or Asia, the PR test is the standard performance test. So some challenges that we've seen over the years. I think a lot of it can be traced back to if you look at the history of the ASTM and the performance ratio testing, those were defined when plants, I like to call them the good old days. They were simple. They were all out in California or Arizona. They were on flat pieces of land. Biggest thing you had to worry about was soiling, as kind of Jim mentioned, and maybe some far horizon shading. You had simple homogeneous block design, easy to do. They had low DCAC ratios, et cetera. Modern plants, anything goes. They're built on hillsides, forests. You got extreme climates now. We see the layouts that come in. I mean, it's almost, you look at them and you go, wow, how could it possibly get any worse than this? And you just wait till the next EPC bid comes in or RFP is released. And that answers the question. High DCAC ratios are really challenging to deal with from a capacity testing perspective, and I'll talk about that in a minute too. But complicated topography, near tree shading, et cetera, are all challenges on, again, this all impacts that base energy model that, we have to work with and defines, kind of the testing parameters. And then you can throw in smart, tracking algorithms as well. So some challenges that we've seen, again, as mentioned, these testing guidelines were developed for simple, sunny PV plant locations. They are heavily weather dependent. You need basically some clear sky conditions. High DCAC ratios often limit the data collection. And I got an example here. This is just a clear day from recent tests we did. Site clips at, this solid sunny day. You look at it and go, yay, I got a nice sunny day. When you dial it down and you actually apply all the filtering and everything, you're left with just these little slivers of shoulder data that you can count towards as valid data towards your test. So it can get really challenging, and these can extend even clear days, clear conditions, depending on, again, plant design and things like that can go on. And if you throw in if you get cloudy conditions or partly cloudy conditions, then it can really extend on. The base energy model heavily influences the results. It is, no ifs, ands, or buts about it. That sets the bar, and then what you end up testing to or having to test to is subject to that. So pan file caveats, as Jim mentioned earlier, I'll kind of go into that. We often have to deal with, I call them here, demanding owners pushing for higher guarantee targets. They'll come to us now and they'll say, this is our pro forma model that we're using for our, basis of financing. And we want you to guarantee that a capacity test on that at 100% guarantee, and then with no padding in the model, and have substantial LDs at play, or even make right conditions at play. And I'll be blunt, we're going to say no to that, or have a way to back out, costs that will cost you. if you want to do that. So it's a challenge. And I'll be blunt here too. EPCs struggle to achieve 100% availability often at the time of, by the time substantial completion is scheduled. And what we've done we work with clients, especially ones that want, like, for example, the higher guarantee targets, we'll say, look, let's get the plant up and running. What we'll do is we propose, and we've done this a few times, and I think it's worked out pretty successfully for all parties. Say, look, give us a lower threshold for substantial completion. Then what we'll do is within the next month, 45 days or so, once we get, for example, the IR drone reports back and things, and we can go out and polish off the plant, get it running nice and smooth, and then we'll run your tight, we'll give you a performance test there that demonstrates, a smoothly running plant. So these are ways, again, we work with, everything's different. There's nothing consistent here, and you do what you can, but we try. So here's an example. Eastern US, I'll just call it Project XYZ. This was a recent EPC project we worked on. Incredibly complicated layout. This is on the left is a drone image of the site. And if you can see that little off to the upper right of the picture, there is a little section, that's the same plant. And this is the PVCist shading scene that we generated from this. We imported in from PVCase. Crazy shading, near shading conditions, topo like crazy. The only, I guess, one benefit was it was monofacial. So at least we didn't have to deal with bifacial here. But so in this project, we, again, tier one, a well-known module, tier one supplier. We had a PVCist based energy model, which again we were given OEM PAN files, and we knew they potentially have issues. This was about 3 years ago when we did this. So this was kind of right when the OEM PAN file issue was starting to percolate up. And what we received were the third-party tested PAN files from the OEM after the EPC contract was signed. So this was a stiff EPC contract, and you kind of locked in your base energy model at the beginning. So as soon as we got the third-party PAN files in, you just flip the PAN file in the model, and we instantly saw 1.7% annual energy drop. And for us, I mean, that's bad news, but our challenge was we were testing in plan scheduled testing in February. And this was almost a 3% drop, which matched the test uncertainty allowance we were given here. So this actually triggered for us design changes to mitigate this performance ratio testing risk. So this was a huge deal. And then now the PAN files with and to continue on what Jim said earlier, this PAN file is the key to the module's performance within the PVSys framework. In my opinion, and our opinion, all PAN files should be treated as suspect. These things are not guaranteed at all by the module manufacturers. We've been admonished. I mean, I've talked to them. I mean, as far as I'm concerned, here's an example. Bruno, I think this would be a good addition for you should have, if it's an OEM PAN file, you should have a header on it that says for entertainment purposes only, because that's the only guarantee that you should have there. Thanks. We have noted 1 to 4% drops in annual energy by just, again, flipping the OEM and third-party PAN files. As Jim mentioned, there's a plethora of reasons. IEM loss, low light irradiance, et cetera, are all the things that, they kind of play with. But we highly recommend using trusted third-party testing labs. RETC and CFE are the two we like. And this is due, and again, I say trusted here because we have seen suspect third-party tested data come from Asia region testing labs. And any legitimate PAN file that's been tested by or provided by a third-party lab there is always a report generated. Always ask for that report for review, because at a minimum, it gives you an idea to check the sanity of the testing methods, the results, make sure they line up with what you're seeing in the pan file. Again, because these pan files are not, there's no locking mechanism or a way to keep them, locked down or anything. Anybody can go in and modify anything in it at any time. And now, as a rule of thumb going forward, we independently, as Jim mentioned, we take modules as soon as they get delivered to site, whether we procure them or not, we send them to third-party labs for our own independent pan file analysis. That'll allow you the most accurate, again, bill of materials based on the modules you actually have delivered on site. Short-term energy testing. The PVSys, this is a simple concept in theory. Running it's a little trickier, but in what we do is you take the base energy model that you have that often defines your capacity test, and now you run it with the on-site weather data over a fixed amount of time, usually 2 to 4 weeks is what we typically see. And it's run after substantial completion and before final acceptance. So sometime, after the dust is settled and the plant's running, hopefully smoothly. Sometimes guided by IEC standards, most of the time not. And the benefit or the beauty, I believe, here is it gives you a real world evaluation. Again, it's short term. It's not a year, and I understand, I agree. I think a year would be ideal, but no EPC is going to sign up for a year energy test. That's O&M. But it gives you a short-term evaluation. You can check, again, the shading model, and it runs from sunrise to sunset. So we're not filtering down the data like you do in a capacity test. It's just some ideal window. We're running it sunrise to sunset. And the result, or what you want, is you get a bucket of, at the end of your time period, you got a bucket of measured energy, and all you want to do is your goal is to be higher than your bucket of predicted energy. So again, driven by that PVSys model as well. We are seeing this more and more common in EPC RFPs, and often paired with capacity or performance ratio testing. Another example, this is, again, I'll take it from the same project I showed earlier, the complicated one. What we did was we took the standard hourly PVSys modeling practice for an energy test, and we compared it with a novel kind of sub-hourly clipping method. And I'll show just a snapshot of the results here. But the sub-hourly clipping one, this is a concern we've seen for a while, and it's well known in the industry, but if we do a lot of EPC projects in the southeastern US, you pick the wrong time of year to run energy tests, and you'll get partly cloudy conditions every day. And the base energy model will overpredict if you just take the standard process of using hourly resolution data and running it through the model. And if we've got and we're seeing, LDs and performance guarantees tied to these. So it's a risk to us. So we've been looking for ways to, mitigate this. One method we looked at is to just take the 1 minute site resolution SCADA data, because that's what we typically work with for both capacity testing and energy testing. What you do is you create 60 input files into PVSys based on that minute's position in the hour. So for example, at 5 minutes, I'll take every 5-minute value at every hour and put that into one file. And I'll take all the 6-minute values and put them into hourly files there. The trick is you got to apply the appropriate time shifts within PVSys to get a reasonable answer out. And then you just batch process these. Once you have the system set up, it's actually not that complicated to do. Again, you have to QC the data meticulously at the beginning for any energy test. And then what I've seen done, and I like, is you can compare the input, output, you can compare the on-site plane of array data. We don't feed that into PVSys, but you can compare the on-site plane of array data with the predicted plane of array data within the model framework, and then do bias corrections there. So that's what we did in this case. And then beyond that, there were no filtering applied to the results. It's, again, sunrise to sunset for 21 days. And here's an example of 4 days in the test period. We had clear sky conditions on part of the days. And then as you notice, we've got heavy, what I would call sub-hourly clipping potential periods there at the back end of the first day and then the third day, the heavy overcast day on the second, and some ending ones there. So comparing the observed, again, now translated back to coming out of PVSys, so we back it into an hour reference frame. So you just take that data out and you just average it over the hour for each hour, and you get the energy in. We see significantly better on the clear sky conditions. It's about the same, but on the days when you have the partly cloudy conditions, this method lines up really well. And I've been doing this for a long time, and this was one of the more, this caught my eye, and this is pretty impressive. Again, from our perspective, a way to de-risk the underperformance potential for the energy testing framework. So the test period, just quick background here, it was basically about half the time was clear and then half the time was partly to mostly cloudy conditions for the 21 days. Again, our target's 100%. The hourly model PVSys, just kind of running it, cranking it through normally, we were pushing 2% low just for this time period. When we apply the same data, just slice and dice it into the 60 files and run it through the sub-hourly clipping method, we're almost spot on to 100%. These results, they look pretty impressive. We're still evaluating it for, one of these times we'll have to put the rubber to the road and guarantee it. But right now it's looking pretty promising. We're investigating it for both for solar and also bifacial PV projects as well, and seeing similar results. So summary, increasingly complicated EPC solar projects are being accompanied by increasingly complicated and demanding performance testing obligations. An accurate PVSys-based energy model is crucial to the successful project performance and energy testing. Knowing where that benchmark is and understanding what the risk is, and within the model framework itself defines a lot. Trusted third-party PAN files are absolute necessity in my mind for an accurate evaluation of your project's performance. Something I didn't have time to show in here, but something we kind of stumbled across on a recent project where we had mixed modules. We're seeing this more common. They had safe harbored non for solar modules. They were just they were normal monofacial modules. It was about 40% of the site, and then 60% of the site was for solar modules. We cannot model those in the same framework within PVSys. So you have to treat them separately. And that was fine from a modeling perspective. But when it came time to test it for performance tests, and this was, I'll say it was in ERCOT region, the ERCOT would not allow, our original proposal was to just turn off the part of the plant and just kind of run them separately. But because of ERCOT restrictions and the owner wanting all the revenue they could get, we had to come up with a way to test it uniformly at once. And our answer was to turn off backtracking, or turn on backtracking, excuse me, for the first solar section. So the entire site backtracked. And this was an interesting result. I mean, if you look at the energy predictions between the two, when you turn on and off, it's fractional. This actually, and we've used this on another project recently, it shortened the testing timeframe we needed because of the nature of the row and row shading you occur with for solar projects by almost 20%. So it was something impressive for us, and something we recommend now if we know we're going to potentially be in trouble with testing timeframes. Energy testing, again, becoming very popular. And I think again, there may be other ways out there to evaluate it, but from an energy testing framework, you've got to deal with, especially the sub-hourly clipping challenges. That's it.